Okay, so let us look at these applications. So I'll just bring in some problems. I have 4 problems which I thought we can just solve. Hopefully it will not take so long. Okay, so the problems that I have here, I took them from our material, so I will not write this story because you see these are real life problems. They come with a story that we have to go through. Then from this story, you have to pull out some important, say, key information that will help you develop an equation. So I will not write already the full story. Maybe I can just read. So you have all of these stories in your material. Okay, so the first problem that we will solve is in your mystery book, page number 14. So it's number 18. I'll just go through the story, then we start solving. Okay. It says that the rate. Sorry. Okay. It says that the rate of decomposition of radioactive carbon is proportional. So the rate of decomposition of radioactive carbon. Okay. So it's a negative change that we have here. So I'm using R because they talk of some radioactive. You can also use a C. So the rates of course, this is happening over time. So the rates of decomposition of radioactive carbon is proportional. So they do not specify what kind of relationship we have here. So we'll assume direct proportionality. So it's proportional to the amount present at any instance. So let me say proportional to R at any given instant. Right. So this line is enough for us to have an equation to solve. So from here we will get a general solution. When the story continues, it says the radioactive carbon has a half-life of approximately. Now the story starts to give us some conditions that we have to apply into the general solution. Okay, so let us go ahead and try to solve this problem here. So what we therefore say is that okay, so what we say therefore is that we have minus dr over dt, because we have to have an equation to solve. So the proportionality symbol, we always replace it with the equality sign with the k, which is the proportionality constant. So then r. So therefore when we have to solve here, so therefore can see that let us try to remove the minus sign on the other side. So this will be minus kr. Good. Okay, so it's a nice simple problem that we can solve using separation of variables. So let me just do it quick. Since in fact we have 4 problems, maybe we have to move a bit. So then with the separation of variables, we can put in r at the bottom here. The r, this one, they have to separate. Therefore this will be k. So dt will come and sit on this side. So we therefore have to integrate both the left and the right hand side. So we can say plus c. So you remember therefore from the separation of variables, f minus kt plus c. Our special variable r, it only appears once here, so we can easily make it subject of the equation. So what we get, we're getting r is equal to the exponent, so e raised to minus kt. We're supposed to be having a c here, like this, which actually comes with a plus a c. But what we normally will do is we simply can just put a here. You can put a, but also what people will actually like to do in these situations, they will say r naught. Okay, good, just a constant. So what do we have here? So we have a general formula. After we have this, simply just have to go back into the problem. Again, I will try to make it quick so this video doesn't take that long. Shouldn't go above 30 minutes. I always try to target a 20, 30. But of course, in some situations, it really takes forever. Okay, so anyway, so we have a radioactive carbon, has a half-life of approximately 5,600 years. So what is the meaning of this? So this is a condition. Let me just say, let me write it here now. I'll continue here. So they are saying that R is equal to half of the original amount at T is equal to 5,600 years. Okay. So this is the half-life. So half-life of us, it means we now have half of the content left. But what we know is that R is equal to this right-hand side, because this is still R. So it therefore means we can equate the right-hand side of this R. So it therefore means here 1 over 2 R naught is equal to R naught e raised to minus KT. Right? So you can see what happens here is that R naught can, of course, they will cancel. And when they cancel like that, they leave us with 1 over 2 is equal to e raised to minus KT, which, since we are looking for, there's something I'm doing here. T, we have a value for T is a 5,600. That's, we have a value for T here. Then also put a value for T there. Okay, we have a value for T. Okay, so T is 5,600. Yes, good. Okay, so we are looking for K here, and the K we're looking for is sitting far up into the exponent there, so we can only drop it with the log. So let us do that. So therefore we have a ln 1 over 2, so is equal to ln, when you apply a ln on this side, minus K 5,600. So therefore it means our K will be able to drop. It comes with the value of time here. So we have a minus, let me say 5,600 K here. So therefore, making K subject of the equation, you get minus 1 over 5,600 ln 1 over 2. Okay, this is a minus. It's a minus here, but it just seemed to just have as if it's one line. Okay, I don't like it if like that. This is a minus. Okay, yes, minus. Okay, so then you can use a calculator and see what value of K that you get from here. Myself, I have it. I've used the calculator myself. So this is a 0.300 124. Okay. So once we have the value of K, so therefore means we now have a better formula for this problem which we are solving, and the improved value or the improved formula is therefore equal to R naught e raised to minus. So it improved because we now have a value of K here, 0.00124 T. Right. Okay. So we have applied this condition. You can go back into the story and see what else they give us. Okay, so they say now it's a question. So the question says, in how many years will it decay to 20% of its original value? Okay, so it will decay into 20% of its original value. So it's a question now. In fact, let me just go this way again. Let me just continue this way instead of going down. Okay, so now we have to answer into this question. Now we have to give them a solution. So in how many years will it decay to 20% of the original value? So this is therefore means in the 100% that was there, 80% is gone. It means R is equal to 20% of the original 100 of the R naught. So the question is, how long does it take for this amount of material to go away and you only left with 20%? So we therefore are having what? So we therefore having 20 over 100 R naught is equal to R naught A raised to the right hand side now of R. You can see here, this is our right hand side of R. We have a value of K now, so this is a minus 0.000124 T. Right. So again, R naught and R naught can cancel. So basically what we have here, we are having 20 over 100 is equal to e raised to minus 0.0124 t. Right. So we're having the same situation again. We are looking for time here, but what we see is that t is sitting on top there in the exponent, so we have to drop it, and we also can do that just by using the logs, right? So let's try to do that. So therefore Evelyn, since this can simplify, the 20 over 20 to 1, 100 over 20, we say 5, of course. So therefore is equal to, so log will drop this power into a minus 0.000124 t. Then make t subject of the equation 0.000124, then log 1 over 5. So then what is the answer from there? Let me check. It's a ln 1 over 5. So divide by minus 0.000124. So we are getting, the answer is that t is equal to 12,979 years. Okay, so it's really an approximation basically. So okay, so myself I'm getting 3, 4 here. Okay, yes, good. Okay, so this is the answer that they were asking us to find. So there we have it. Let us move on to another exercise. Okay, so there we go. Okay, number 2. So what exercise do we have here? So again, the second exercise is coming from our material. It's coming from a mathematics 3 notes. Then this is page 41. Then it's number 22. So page 41, number 22. Again, I will not write it. So you have the material. So I'll just read. It says, a bacterial population increases at a rate proportional to the population. Okay, so let me use a P, yeah? So we have a change, the population is changing, and the statement just says it increases, therefore this is a positive change. It's proportional. It's proportional to the population. Okay, so therefore it's direct proportionality like this. Then the story goes on and say, if the population triples, etc., etc. Okay, so these are the conditions. So this is all that we need to develop the equation. And then after we have the general solution, then we'll go back into the story and try to apply those conditions, just to polish that, general solution in preparation of some applications that may come after that. Okay, so that what we have here is enough for us to solve, get a general solution. So proportionality sign we always replace with equality and a k, which is a proportionality constant. Then it's a p. Okay, so this is just a simple case of you just have to use the separation of variables again. So therefore must separate, therefore 1 over p dpm, so is equal to k dt, integrate left and right hand side, plus the c, so we get a ln. We have the same equation like the previous problem here, so it's therefore equal to kt plus a c. So p appears once, we can make it subject of the equation, so therefore we're having e raised to kt here, then so goes p naught. Good. Okay, so there we have it. So the next thing that we just have to do is to go back into the story and continue with what the other lines are telling us. So they say if the population triples in 1 hour. Okay, so we have a condition here. They say p is equal to 3 times the original p in t is equal to 1 hour. Okay, it's a condition that we must apply. It will give us a value of k. So let's do that. P is equal to 3 p naught, but p is equal to the exponent. So therefore it means 3 p naught is also equal to p naught e raised to k 1 hour. P naught will cancel. So this will therefore leave us with 3 is equal to e raised to k. So therefore we must introduce a linear so that we are able to drop the k. It therefore means k is equal to ln 3. Good. So we therefore now have improved the equation, which is p is equal to p naught e raised to ln 3, then put it in brackets t. Right. Then just draw a line here. Then you go back into the story. Then they say how many say in how many hours will it be 100 times the original size. Okay, so they say in how many hours will p be equal to 100 times the original size. So it will take how long for this to happen? So this is the question. Okay, so it's simple. 100 p naught is equal to the right hand side is equal to p naught e raised to, we now have improved the version where we now have a value of k. So again you can see they will cancel, and when that happens we'll be left with the 100 is equal to e raised to ln 3 t. Again we have to drop that t there. Of course we have to use a log here, so therefore I have a log 100 is equal to ln 3 times the t, so which therefore means t is equal to ln 100 all over ln 3. So what is this? So what is the ln? 100 over ln 3. So it's a ln 100 over ln 3. So this is equal to 4.19. Okay, let me say 192, but even just 19 is fine. Okay, so this is the amount of time that it will take for this population to be 100 times the original size. Okay, so this is what they ask us. In how many hours would it take to be 100 times the original size? It therefore will take 4.2 hours to be 100 times p naught. Okay, so we can move on. Okay, so we can move on to another kind of a problem. So the problem I have here, I have Newton's law of cooling problem. So let's try to look at that. Of course, I will not be able to solve all kind of cases here. So these ones, they serve as examples. They just give you the example of what kind of problems you must expect under this section. Okay, so number 3. Okay, so this one is not from our book. I will write it. Let me write it. So it says, okay, let me just write it. It says an object goes down 100 degrees Celsius to 60 degrees Celsius within 10 minutes. Okay, so within 10 minutes of being placed in a stream of air at 20 degrees Celsius. Right. Then the question says, determine, so it's temperature after 40 minutes. A very simple exercise involving Newton's law of cooling. Okay, so try to solve it, see what we get. Say the solution here. Okay, it says an object cools down from to some temperature within etc. etc. Okay, so the way these problems are is that the first thing that will happen is that the story tells us the equation that we must solve. After we have the equation, which will get the general solution for that equation, then the story will start to give us some conditions which we have to work with. Of course, put those conditions into the general solution that we have just obtained, which then prepares the general solution for some applications that we have to apply afterwards. But the Newton's law of cooling is a bit different in that setup, because what we see from the story that we have here, we don't get any information about the actual equation that we must solve. The left-hand side is equal to what? Proportional to what? The right-hand side, so that we can actually develop an equation to solve and get a general solution. So the reason being really is that it's a well-known law. So somehow it is pointless. It is pointless for the story to say, some temperature T, okay, of course over time, okay, is proportional to, and etc. etc. It's proportional to the difference of the temperature of the object minus the temperature of the surrounding. So it's somehow it doesn't give us this info, because again Newton's law of cooling is a well-known formula, or say is a well-known law, so we just have to apply it. We have to apply into this problem. Okay. But again, what I think we will have to be careful with is that this doesn't mean that Newton's law, this formula, is included in the formula sheet. No, it is not there. You just have to remember it yourself. Okay, so you just have to remember it yourself. Okay, so let us solve it. So what we have to take from the story that we have here is that the temperature of the object cools down. Okay, it cools down. That is important, because what it tells us is that in this Newton's law of cooling, the change is negative. Okay, that's what we get from the cool down. Because we have one formula here. It's called the Newton's law of cooling, but it works for both cases, where the temperature goes down and also where the temperature of the object increases. We use the same formula. Okay. So therefore this is equal to, that part of is proportional. I'll just omit. I'll just replace the proportionality constant. I'll replace the proportionality symbol with equal sign and a k. Simply I'll start from there. Okay, so this is what will be it's proportional to the right hand side, which is T minus say TS, which is the temperature of the surrounding. Okay. Yes. Okay. You can also use a symbol here. For instance, when I was solving this problem the other time, I used a tau, so it will be the T over D. So is equal to K T minus tau. Okay, it's the same thing, right? So assembly means TS is equal to tau, the symbol here. Okay. Okay. So this is what we have. So let's just try to solve and get the general solution and come back into the story, because the story only have conditions, and then it's then ask a question afterwards. Okay, let us get the general solution. So therefore we have a dt over dt, dt and a dt is time over temperature. Okay, is equal to minus k t minus ts, right? Then we have options. You can use a separation of variable method, or you can use integrating factor method. Right. So let us use, in fact, for this one, we have done two problems where we use a separation of variables. How about we use integrating factor method for this one? So therefore is equal to k ts, right? It's almost like a 5. No, it's a s. This is what I don't like. Someone can easily think this is a 5. When there is another problem that I will solve, which is a Newton's law of cooling also, I will change the ts into the symbol that we normally will use. Okay, this is not a 5. Let me continue with the ts, because I've already started with it. Anyway, so integrating factor, therefore it's if is equal to e raised to k dt, so therefore equal to e raised to kt. Right, so therefore means it's t e raised to kt is equal to, then the right hand side is only having constants. Okay, so therefore having k there, it's a constant, surrounding temperature is a constant, because of course we are working on the same system. The temperature will only change when we go into another system, therefore different conditions, therefore the temperature of that environment may be different. Otherwise, for now it's a constant, so I will put it outside of the integration sign. Therefore I put my integration sign, and what do I have inside? I have if, so it's e k t dt plus c. Okay, we have to integrate, so it's a kts, so therefore it's e raised to kt all over k, integral of exponent, just obvious. So we are therefore having, let me put it close. I think I wrote my equality sign very far. Okay, so we can see k and a k, these two will cancel. So therefore we'll be left with Ts e raised to kt. Again, it's not a 5, it's a Ts, surrounding temperature. Okay, plus C. The T here appears exactly once, so you can easily make it subject of the equation. So therefore this will be Ts divided by this exponent. This one will therefore cancel, give us a 1. So therefore it's a plus C e raised to minus, because it's from the bottom, kt. Right. So we get a general solution that we have here. So now we have to go back into this story that they gave us. So they are saying, we got not so far, it's just here. They say an object cools down from, therefore T naught, when time is equal to 0. T for temperature. Temperature is 100 degrees Celsius. 10 minutes later it's 6. Okay, let me try to put it close here. They say T is equal to 100 degrees Celsius when T is equal to what? 0. What are they using? Minutes. Therefore, let me say 0 minutes. Okay, so this condition will help us get a value of K. No, we will get a value of C. This is the beginning. Okay, so let's go ahead and try to get it. 100. If we may omit the symbol degrees Celsius, I'll just say 100 is equal to Ts. The surrounding temperature is given. They say, the story says, within 10 minutes of being placed in a stream of air, 20 degrees Celsius. Okay, temperature, this 20 degrees Celsius is the surrounding temperature. Therefore, plus C e raised to minus kt is 0. Right, okay, so therefore means C is equal to 100 minus 20, which is equal to 18. This gives us a better equation because we now have a value for this variable. Let us just put a value which belongs here, which is at 20 degrees Celsius. And then C have a value now. It's 80 degrees Celsius e raised to minus kt. It's always like that. C is a difference of T minus Ts. Okay, so then the story also says it's 100 to 60 within, therefore 60 corresponded to 10 minutes. So we therefore have another condition here that T is equal to 60 degrees Celsius when T is equal to 10 minutes. Right? So what do we have here? So therefore means now we have 60 is equal to 20, doesn't change. We're still on the same system. Therefore plus 80 e raised to minus k. Time is 10 minutes. This condition will give us a value of k. So therefore I have a 60 minus 20. Therefore means we have a 40 here is equal to 80 e raised to minus 10k. Therefore, how about we try to move faster? This is a lean 40 over 80 equal to, then we have applied the log on the other side also, therefore get minus 10k. So from here, you can easily see that k is equal to 0.0693. Okay, good. Right. So it's a 6. Yes, 0.0693. Okay, perfect. We therefore are getting, so what are we getting? So we therefore are getting a better equation, which is a 20 here plus 18 e raised to minus k. It's a 0.069315 t. Okay, yeah, this is what you. Oh, okay, I've just read. Okay, let me just. It's fine. Just complete it, write everything. So this is the equation that we get. So the next thing that we have now is we have. So already we have obtained all the values that we had to get from some given conditions. Really now what we have to do is to apply this equation. So let us see how do they want us to apply it. So they say determine what the temperature after 40 minutes. Okay, it's a simple application. So they say, okay, now you have the equation. How about you apply it? They say find the temperature in 40 minutes. So therefore it will be 20 plus 80 e raised to minus 0.069315, then times the 40 there. Then what do we get? You get 24.999, etc., which is simply just, I would say, 25 degrees Celsius, approximately 25 degrees Celsius. Okay, so this is the application that we have. There's a time within this problem where I stopped. I see that this recording is becoming long. In fact, so what I think, let me check how long is it now, if it's too much. Okay, so I think because of the other application I have is simply just the Newton's law of cooling. It's however for a can coming from a fridge, etc., etc. How about I leave that for you to solve. The next problem I thought I will solve, it's a problem 40. It's from page 41. It's number 27. Simple exercise. You can solve it following exactly the same steps as what we have here. You'll get the answer. The only difference now is that the change that is happening into the temperature is increasing. So temperature of the object is increasing, which is just the opposite of the problem that we were solving in this recording. Okay, so myself, I will stop here. So try to solve that one, number 27, in page 41.